Hello everyone and welcome to today's webinar. I'm Tom Floyd. I'm your moderator for today's session. With me today is Sue Poniatowski from High Speed Data Path Applications.
Morning.
Welcome, Sue.
Thanks.
And Alex Tan from High Speed Data Path Marketing. Welcome, Alex.
Good to be back.
Good to have you back as well. Lots of great stuff to cover today, as always. For those of you who are joining us live, we definitely want today's session to be interactive. So if you're logged in, just type your questions directly to me, and I'll ask those on your behalf. And with that said, I think we can go ahead and get started. So take us away.
Super. So today we're going to talk about the FPD-Link III solutions. This is the third in our series on FPD-Link interface products for automotive applications. And we're really excited to talk about this because what we're introducing here is a new family of parts. Specifically, there's two chipsets, the DS90UB 901, 902, and the DS90UB 903, 904. As we mentioned, my name's Alex Tan.
And I'm Sue Poniatowski.
So the objective here, first we want to explain the automotive applications for FPD-Link III. We want you to know what are the key system benefits of these chipsets and to discuss the main features and their value. And as I mentioned before, it's very important to introduce the new FPD-Link III technology. So we'll start with that.
Okay, so first off, what is FPD-Link III? Well, what this is bringing to us is all the great features we had with FPD-Link II and adding some more. So we preserve the high-speed forward channel serialization that we had with FPD-Link II. And now we're adding low-speed bidirectional control and as for I2C signals as well as GPIOs. And the important thing here is this information is transmitted continuously full duplex on just one pair. So this is replacing the multiple interfaces or wires with just a single pair in the system. The whole idea here is doing more on two. The diagram here is showing a simple explanation of what's going on here. We have data coming in at 16 or 21 bits of video data being transmitted in the forward direction, and then the deserializer takes that and sends it to a controller or a display device. And at the same time, we're sending control data backward and forward between the serializer and deserializer. This is the I2C and the GPIO data.
That's right. And just to remind you, in the previous series, we talked about the great technology we have for the FPD-Link II family, and that's the forward channel. And this builds on top of that FPD-Link II technology. So we're very excited about this. And let's see. First, I think we'll talk about the different applications it goes into. So there's really two different automotive applications. First is on the driver's assist side, and the second is on infotainment. For driver assist camera systems, you see in our diagram on the right that the vehicles are getting more and more cameras. They're getting cameras on the front, they're getting cameras on the back and sides. We are already in systems that do that. These devices are targeting rear view and side view cameras. They're targeting lane departure warning, parking assistance, blind spot view, and they support many of the common imager resolutions, including 640 by 480 at 60 frames per second, 1280 by 800 at 30 frames per second, and also new megapixel cameras that run at 30 frames per second. And if you want to talk just quickly to the diagram.
Sure thing, yeah. So what we're starting off here, if we look on the right of the diagram, we have the microcontroller, the ECU, controlling all the information and the processing that's done. From there, we have a deserializer, which is going to accept the data coming from the camera. So we have the camera on the left to the deserializer sending video data, as well as communicating I2C. And then going across the link, FPD-Link III, we have the forward channel data and the bidirectional control data. This is I2C. And the deserializer takes the video data, forwards it to the microcontroller. Microcontroller in turn is sending I2C commands back and forth with the camera over this virtual bidirectional control link.
Now, are both SerDes chipsets targeted at driver assist systems?
Good question.
Yeah, and primarily the DS90UB 901, 902 is targeted for the driver assist systems. We have some features we'll talk about later that are specifically targeted to cameras. However, the 903, 904 can also be used in systems which require the higher bit depth supported by the 903, 904.
Okay, gotcha.
And Tom, this actually represents the first chipset that's really designed from the beginning for these type of driver assist systems.
Great.
It's a really big market. If you have any type of cameras on your car, you see very quickly.
Which I do.
Oh, then you know what we're talking about, right? very quickly you see that the cameras are a very important part of safety, and often how the automotive manufacturers will sell or promote their vehicles.
Got it. Okay.
Sorry, go ahead. Okay. So then the next opportunity or application that we're focusing on is displays, and particularly touchscreen displays. With this bidirectional control channel, we can support a touchscreen display for the central information. That's the navigation unit that's in the middle of the car. Also just for navigation systems by themselves that don't have maybe as much video, rear seat entertainment, all sorts of places where you can put a display in your car. These have very good links for it. And common resolutions there are 640 by 480 at 60 frames per second, 800 by 480 at 60 frames per second, and also 1280 by 480 at 60 hertz.
Now, are both of these chipsets also right for touchscreen display as well?
The 903, 904 is really targeted for touchscreen and displays.
Okay.
This is primarily because of the higher color depth that's supported, so most displays do require the 18-bit color depth supported by the 903, 904.
Okay.
Okay. And if we want to do just a quick review of the application here, what we're showing in the bottom graphic here is first starting off with a graphics processor that provides the data, and then you can see the data interface that supports 18 bits of color plus the synchronization signals being sent from the serializer to the deserializer over the FPD-Link interface, and then going on to the LCD display. Now at the same time, the graphics controller is able to read touchscreen information from the display side, and that's where the I2C and bidirectional control come into play.
And that's really the difference with these new chipsets.
Exactly. Now we're sending all this control over the same set of wires that we're sending the video. So there's no need for a separate control channel between the host side and the display.
Okay.
So let's talk about the advantages. The key thing, and if there's one takeaway that we want you to have when you from this webinar, is really in terms of how the bidirectional control works. The idea is that both the video and the I2C bidirectional control are on the same link, and that's important. Also important is the approach that we've taken, and it's unique to National, is continuous. It's continuous communication in both directions, and what that brings you is low latency. And it brings you a low latency both for the bidirectional control and also for the GPIO transmissions. It's EMI friendly so that people who are designing systems can meet the EMI requirements, and that's crucial for automotive applications. And finally, the upshot of being able to put all of these capabilities into one pair is that it reduces the cost and the weight of the cable harness, which is an important part of the systems. And I just want to emphasize, this technology is not dependent on blanking periods. Other advantages in terms of the details for the I2C, we support up to 100 kilobits per second on the I2C. We have programmable I2C addresses, and we'll go into more detail on how you use that in an application in a slide further. And we have a single I2C hardware address pin. The technology is built on the great features of the latest FPD-Link II part, so that means it included all of the great EMI enhancements that we talked about last time. And also, these parts support from 10 to 43 megahertz pixel clock, so a wide range of resolutions.
Coming back to one of the advantages that you show at the top, not dependent on blanking periods, can you tell us a little bit more about why that's important?
Sure.
Yeah, sure. So if we are continuously sending both GPIO signals, so control signals, from the system host controller to the remote device, and we're also allowing a continuous stream of I2C control data to happen. If we were to have to wait for video blanking, that would slow down the transactions and would also limit the timing of the control signals that could be sent to the remote devices. This is especially critical in camera systems where you have multiple cameras that need to be synchronized.
Oh, okay, gotcha.
Okay, sorry. So let me tell you a bit more about the DS90 UB901-902, the integrated bidirectional control channel. What we've got on the upper right-hand side is an example of one of the car driver assist systems. In this case, what this is coming from is a forward-looking camera that's probably placed behind the rear view mirror in the car. And it's actually looking at the road ahead of the driver and identifying where the lanes are. And those green boxes are showing where it's seeing the lanes. And it uses this to let you know if, say, you're driving on the highway and you start to get a little tired and you move over, get closer, it'll make a noise or blink or somehow let you know you're driving off the road, which is very important for long-distance drives.
Definitely.
And the diagram on the bottom kind of gives you, from a system perspective, where these parts are targeted. This diagram shows an entire network of infotainment and camera systems, and the area in green is showing multiple cameras going to a camera ECU that's processing the information, and then it provides that information over to the head unit and also to the automotive control systems to keep you safe. Sorry, go ahead.
So thanks, Alex. That was a great job explaining how these parts are used in systems. I'm going to talk a little bit about just the details here. First of all, the 901, 902 supports 14 bits of color as well as the sync signal. So this is ideal for cameras where typically today 10 to 12 bits, but we're providing some room to expand to 14 bits of resolution. The 4-bit CRC, this is an error detection for both the video and the control channels. We actually monitor the data and flag to the user if there's been any corruption of data for some reason on both directions, the video being sent from the camera to the processor or any control information. And as Alex mentioned, these processors are often making very critical safety decisions based on the data they're receiving. So it's important to have this error checking to flag to the system if anything has gone wrong so that they can make adjustments in the type of safety decisions are being made. Programmable GPIOs are available, and this again just allows the camera and the host controller to talk to one another. Synchronization signals can be sent from the host to the multiple cameras and make sure everything is coming, all the data is coming in at the same time and synchronized. And these GPIOs can switch, as we note here, at about 58 kilohertz maximum frequency. So that allows a lot of flexibility with transmitting this data.
And both of those are particularly unique to the 901, 902.
Yes, they are. Yes, they are. The I2C slave address remapping, what this does, it allows the system to have multiple cameras attached. They could all have the same I2C address. And this avoids the problem of having single address for all the cameras. It allows a remapping to a unique identifier so that the host system can independently address each one of these cameras, even though they have the same address. And then finally, just the logistics of it, this provides a very small serializer footprint. This is a 32-pin LLP package. It's 5 millimeters by 5 millimeters, and it fits very well inside of the small camera modules.
And although that may seem like a small thing, no pun intended,
Yeah, no pun intended.
it's actually very important because the systems that people are developing are in areas that are affect the design of the car. So they're in areas that are, say, like I mentioned, behind the rear view mirror, where they need to make the camera as small as possible. Because you don't want to go and buy a very nice high-end sports car and have a big clunky black plastic sheath around your rear view mirror that the people from the outside see, you know, a big black mark on your window. It seems like a little thing, but for the automotive manufacturers, that's key. And anything they can do to get these systems smaller is very important.
Got it. Makes sense.
Yeah. And again, then, let's talk about the display side. So the DS90UB903-904 provides the same integrated bidirectional control, but really targeting displays. And what I'm showing here in the picture on the right is an example of one of these automotive displays. This one is a pop-out display, meaning that it's in the center of the car, but when you turn on the car, this slides up so that you can see it. So it's small, but it has to be very clear and very clean. And if it's a touchscreen display, you need to be able to send the information from where you're touching it back to the system. And really, where does this play? If we go back to our diagram in the bottom shows a built-out system that has a number of different displays. And this is actually fairly common in high-end cars and becoming increasingly common across the platforms. So this has a head-end unit that's driving the navigation display, which is in the center of the console. It has a cluster that's driving the instrumentation. That means that actually your dash is also a big display, maybe a 12-inch display there, and potentially a heads-up display, which is either presented on a separate auxiliary display or maybe even projected onto your screen, showing you maybe like that display we saw earlier, actually putting those green squares on your screen so you could see.
Interesting.
Yeah. And then in the back for the kids, you've got the rear seat entertainment, and that's where you've got videos, and you've got to have your SpongeBob SquarePants video and everything very nice and clean, and allow the kids to play games and what have you. All of those links are also used or addressed by these products.
Question that just came in: does switching
Sure.
to 58 kilohertz mean 58 kilohertz pixel rate?
No, it doesn't. This is referring to the speed of the general purpose I/O switching.
Okay.
The pixel clock rate, remember, is coming from the serializer, the forward channel, and that can go up to 43 megahertz pixel clock.
Okay, gotcha.
And the switching rate for those GPIOs is a feature of the bidirectional control channel.
Yeah, and just to add to what Alex was talking about here, talk a little bit about the specific features of the 903 and 904. These do support 18-bit color. This is very typical for display applications. And also we have dedicated inputs for the synchronization signals, H-sync, V-sync, and data enable. On this chipset, we offer a dedicated general purpose input and general purpose output. So there's a channel back from the deserializer to the serializer. In touchscreen applications, this may be used as simply as an interrupt to let the host device know that there's touchscreen information that the host then goes and reads over I2C. And then we offer the error checking with CRC over the back channel.
Yep. So let's talk a little bit more about this bidirectional control channel. Like I mentioned earlier, this is really the key feature that we've put in here, and it took a lot of effort. This is a novel approach that provides transparent access to the I2C over the FPD-Link III the FPD-Link III technology. So from a diagram perspective, if you looked at the two yellow boxes, the box on the left is the serializer, the box on the right is the deserializer. And in this setup, what we're showing is that the control from an I2C standpoint is on the deserializer side. So that might be, I guess, a camera, right?
That's right.
So in this case, the camera has some sort of ECU that's controlling it. It's acting as the I2C master. And oftentimes in older systems, without this technology, this would have to go to another automotive bus. They hardly ever run I2C raw over an automotive system. They'll take it to CAN or LIN. So there's additional components that are required. In this case, instead of doing that, they put it on the I2C at the deserializer. The bidirectional control channel basically acts as a bus, and it gets received at the serializer, then sent to the slave. So you've effectively got the ECU at the deserializer side controlling, say, your camera, imager through this. And it's basically transparent with the caveat that we can't break the laws of physics. There is a distance physically on that wire, so that imposes some constraints on the I2C operation.
Okay. So with this approach, you're removing some of the wires, right? Does this reduce the cable cost and the weight too?
Exactly. That's exactly the intent of this. And it's back to that theme of doing more on two, right? We know that our customers are driven to reduce the system cost overall, and reducing the size of these cables and reducing the weight helps not only with the cost, but with the fuel efficiency. And I mean, Alex can probably give you some more detail, but there's a huge wiring harness in these automobiles, and the harness is a huge cost contributor.
That's right. Of electronic components, just recently went to a IESF conference where they were talking about that the electronic harness, the cable harness itself, is usually second or third in terms of the weight and in the cost contribution of electronic equipment in the car. So although you're thinking maybe it's just a little cable, when you put it all together, this is 200 pounds of wire that's driving the size of the structural members of the vehicles. It's a big concern for automotive developers.
Okay, got it. Another question that came in, I can see the question here. You mentioned GPIO availability as well. What's the interaction with the I2C interface? Is there any?
No, actually there's no interaction other than they're both sharing space, let's call it space, time slots on the backward control channel.
Okay.
So the I2C information comes in through the I2C port, as you can see on the deserializer, and then the GPIO data will come in on a separate pin on the deserializer, and that's all effectively packetized and sent over the low-speed back channel.
So that GPIO is basically guaranteed.
It's guaranteed, yeah. It runs regardless of whether the I2C is being driven or not. The GPIO channel is always free and available.
Okay.
That's a good question.
Great.
Okay. So now let's talk a little bit about how this bidirectional control channel really works. And here's a diagram that really illustrates the basics of what's going on. Let's start off with the high-speed data here is indicated in blue, and the low-speed control data, or we call it back channel data, is shown in orange. And what you'll see here is that the forward channel driver is sending the high-speed data, and the forward channel receiver, which is in the deserializer, receives that. At the same time, now we have the back channel driver sending data from the deserializer, and this is your orange low-speed data. Back channel driver sends the low-speed data across the same differential pair to the back channel receiver. So the key thing to know here is, I think Alex has brought the point forward, we've said it again and again, This is continuously transmitting data in both directions over a single pair. That means that the forward channel driver and receiver are active at the same time that the back channel driver and receiver are active.
And this is a national patent pending technology that was developed in-house.
Oh, great. Excellent.
All right, so a little bit more about the performance of our bidirectional control for automotive systems. We've mentioned before, this is continuous, this is EMI friendly. Let's look a little bit more in detail. So again, everything's over a single pair. We've broken this up a bit, again, using the blue to represent the forward speed, high-speed video data, and the orange to represent the low-speed back channel data.
So if you could, for the folks that maybe aren't as familiar, explain why there's that blanking period in there?
Oh, sure. So traditionally, video has what they call a blanking interval, and this occurs with every horizontal line, as well as with every vertical frame. So at the end of a line, there'll be a time period when no data is sent, and at the end of the frame, there will be a time period where no lines of data are sent. And this really goes back to the legacy of how CRTs were driven, where there was a beam actually kind of drawing the image on the display. So at the end of a line, the beam would have to retrace back to the beginning, and that's your horizontal blanking time. And at the end of your frame, the beam would have to retrace from the lower right-hand corner to the upper left-hand corner to start over. That becomes the vertical blanking. And this has just persisted, just for legacy reasons, into LCD displays where the blanking intervals really are not needed or can be very, very small.
Okay.
Okay. So what we're looking at here is showing the forward channel data and illustrating here a blanking interval, and then showing that the low-speed data is being transmitted continuously, whether we're sending video data or in blanking where no video is being transmitted. The EMI friendly, what this means is you can see the back channel data is switching equal and opposite on both the positive and negative of the differential pair. What this means is we're not doing any changes to the common mode signal of the differential. Low common mode change means no additional emissions.
Okay. And this technology was designed from the ground up to be have as little impact on EMI as possible, and we have data showing that there really is no impact on EMI.
Exactly.
So this allows signals to go in two directions at the same time?
Exactly. So this is back to this continuous, full duplex transmission. Yeah.
Okay.
Yep.
Got it. Great.
And this brings us back to kind of to the low latency. The fact that we can send control data at the same time we're sending forward data means that there's a low waiting period. There's no waiting for blanking. We have the I2C data and any of these critical general purpose I/O signals being sent in real time. So as we mentioned, there's no waiting for blanking intervals, and this really makes this ideal for situations where you want to synchronize, for instance, multiple cameras. So you want to send out a synchronization pulse from the host controller to, say, 3 cameras on the far end. This can all happen without being dependent at all on video timing. Now let's look at a couple of other bidirectional control systems and some of the restrictions that they may have on their capability. So these are things that National has chosen not to do that are being implemented by some other solutions. In this first case, we're looking at the video blanking restriction, sending bidirectional control data only during vertical blanking. And so what you see here is, again, we're illustrating the forward high-speed data and showing the blanking interval. In this case, this is referring to vertical blanking, so once a frame, at the end of every frame of data that's being sent. So frames are
what would that be?
60 frames a second, or for cameras, sometimes 30 frames a second, which means you can only send information back 30 times a second.
Okay.
Okay. And so what they're doing here, it's pretty straightforward, sending the data back when no video data is going forward. So you're either going in the forward direction or going in the backward direction. And what this really does, it means that you have to have video blanking. So it restricts to systems that do support video blanking. And in multi-camera systems, you lose some of the flexibility for synchronization.
And maybe this could, if they need to have something more continuous, they might have to buffer, or they'll have to have some sort of approach to know when they can actually send data.
Exactly, right? Exactly. It puts a little bit more burden on the other parts of the system to accommodate for the lack of real-time synchronization signals. And just a couple other comments. Some of the multi-camera systems require a separate I2C mux. This alludes to the comment we made earlier, where we have the ability to remap common addresses to unique addresses. A lot of the alternative solutions don't have this capability. So there's actually an additional device and additional cost associated with supporting multi-camera systems.
If they take this approach.
If they take this approach, exactly. And as we noted, this approach is not used in the national chipsets. We send everything continuously regardless of what's going on in the video.
Okay. A couple questions that came in. First question is, how do you extract and separate the two data streams?
Well, as Alex mentioned, this is really a patent pending technology, so we really can't go into the details of how we're achieving that.
Okay, got it.
Magic. Right.
Yeah.
All magic, without breaking those laws of physics.
Exactly.
The next question is, what would you say is our biggest competitive advantage?
I think the biggest competitive advantage is the continuous back channel. And then just allowing the flexibility of the user to have complete control, independent of the video data coming in, complete control from the host side to the remote.
Okay. It both simplifies the design of a challenge from the engineering perspective, but it also allows the people who are developing these systems to do things that they probably couldn't do otherwise.
Okay.
So there's really a lot there, and once you start explaining to people who are developing these systems how it works.
Got it. Okay. That's it for now.
All right. Okay, and then we'll talk about one other scheme that's provided, which has its own negative effects, and that's using common mode modulation to transmit the back channel. So as you can see in this example, back channel data is transmitted continuously. However, it's at the cost of additional emissions. In this case, the common mode signal of the video data is being modulated by the back channel. And this creates what we're showing kind of in the red trace here, a common mode modulation. And common mode modulation translates directly into increased emissions. So although you do get a continuous back channel, the limitation here is EMI mitigation. And this can be very costly, not only in terms of adding additional components to the board, but also in terms of schedule and getting to production release. And again, this is not used in the national chipsets.
That's right. And this is very serious because EMI is safety critical. I mean, look at the problems that they're seeing right now with certain vehicles. Look at just the challenge. Think of it in terms of if you're putting your camera up here, you're putting your camera in one place, or you're putting your display in a place, and you're drawing a line to somewhere else. If you generate EMI, you could be impacting something else that either is important to the drivability of the car, or you might be just knocking out radio. I mean, that's a big deal too. The other part of this is turning it around susceptibility. What happens if you get hit by radio? I mean, what happens if these systems get impacted by radio or by people driving? You don't want when they hit the brakes that all of a sudden your navigation system has ugly.
That would be bad.
In there. Yeah, it would not convey the feeling of a high-end safe vehicle. Yes, exactly. So this is a very important and key consideration for developers.
Okay.
So really what we're talking about now, we're going to talk specifically about multi-camera systems here because I think it deserves some additional discussion on how these parts, and particularly the 901 and 902, are suited for and what they bring to multi-camera systems. So first there's a set of features that really have been designed and developed for these multi-camera systems, and also then I'll talk a little bit about the applications that they're going into because it's really exciting stuff.
Okay, so walking through the features, as we've said again and again, we have a continuous back channel, and programmable GPIOs are sent over this continuous channel to specifically support synchronization for multi-camera systems. The I2C slave address remapping, where we reassign the addresses for cameras, so common camera addresses can then be remapped, and individual control can be sent to each of the cameras. This also allows the side benefit of when repairs are needed, if there's some problem with the camera, a generic camera module can be added, and there's no need to worry about what the address is of that camera. They can all be common, and it's all handled with the programming of the deserializer.
Okay.
Okay. And then the CRC checking on the video synchronization, I2C, and GPIO data. So basically, if there is an error, that's flagged to the host processor, and the processor can react accordingly to make sure that any data that's used for safety decisions is correct. And then finally, the CRC checking on the GPIO and I2C on the back channel data.
And the CRC checking is is really key for these camera systems, and I think that this will become more important going forward. As these systems get tied closer and closer into the drivability of the vehicles, they're going to come under, there's a set of specifications called the AEC specifications that really define how your availability and just how much you can rely on them, and whether or not you know there's a problem. Think of it from a driver perspective. If you're driving and you've got a pedestrian recognition system that can tell you if there's children running near your car, and you come to rely on that, you need to know if there's a problem with your camera so that you don't
hit a child.
Hit a child. I mean, it's very serious stuff, right? Absolutely. So from an application standpoint, how are people using these multi-camera systems? What are you going to get from it? Well, some of the things I've seen and are available in some high-end systems now, one is image stitching. That's where you have multiple cameras looking in different directions, and you take the video or the picture from the different directions and stitch that into one picture. They use graphics processing to give you a top-down view, and then they put a little cartoon of where your car is. And that way, when you're parking into a small area, it actually is very natural. It almost looks like a computer game. You pull in your car and you can see
like it a little bit.
all the way around your car. You know where the lines are. You can line it up perfectly. It can be a great aid, and that's one of the immediate uses of these systems.
Okay.
Also, there's stereo cameras where they put two cameras in a direction, either looking backwards or forwards. And really, the idea with the stereo camera is now you can see distances. You could judge the distance, just like we do with our eyes. And also, for machine vision systems that are looking for dangerous situations, it's actually fairly easy to see something going across, because then you could just look at the change in the pixels, and you can calculate how fast, say, a vehicle's moving or a bike or something. Something coming at you dead on, if you have one camera, you can't tell. At least from a machine vision standpoint, it can't figure out how far away it is and how quickly it's coming. So there's certain types of accidents or dangerous situations that require stereo cameras. And those cameras need to be synchronized very closely.
Okay.
Follow on, another application are user selectable cameras. You've got multiple cameras. An example here is, let's say you've got a off-road vehicle, and you are off-road and you need to look in front of the vehicle. There's actually regulations that say you have to stop your car, get out, look, make sure you're clear. With these type of selectable cameras, you could actually choose the camera in the front and look down. Or if you're not an off-roader, and I've never driven my car off, the closest I've been to off-road is gravel, right? Another situation is, let's say that there is an obstruction near the front of your car at a turn. If you use a user selectable camera, you could actually use the camera that's looking around the front and have basically the viewpoint as if you were at the front of the vehicle, instead of being hidden behind a big SUV or something where you can't see what's coming.
Interesting.
And then the idea with all these systems is that eventually you'll have a car that's uncrashable. That even if you tried to, it would know that it's dangerous and make sure that you don't hit things. In which case, forward and rear cameras are used for detecting hazards and obstacles, and that's including things like the lane departure warning, and also things like I've seen systems that read the speed signs and give you what was the speed of the last speed sign you passed. Huh. So that's not a...
keeps you honest.
Yeah, exactly. Well, it keeps you honest. I think maybe it keeps you
informed.
So that when you get into that speed trap that goes down to 35 miles an hour, you can see that it was really there, I suppose. But there's all sorts of really...
Like it or not.
Exactly. But there's all sorts of really exciting things happening with that.
Yeah, definitely.
A question that just came in. Are we
Sure.
engaged in any of the processor, video, or camera companies?
Oh, yes, absolutely. We're working very closely with on both sides, on the processor side and on the imager side.
Okay, great.
Okay. That's more. Okay, so we've been talking about all these multi-camera systems, so I just wanted to show you an example of what one might look like. And in this case, what we're showing are 3 cameras being controlled by a single microcontroller. This could be an FPGA. And the important things to note here, I know there's a lot going on here. First is that the common I2C bus, and you'll see that connected from the microcontroller to all 3 of the deserializers. And the unique thing here is that everything is independently addressable. So as we mentioned earlier, both the serializers and deserializers have programmable addresses. So there's a single pin that can be controlled via resistor network to select one of seven unique addresses. This means you can have 7 different serializers, 7 deserializers in a system, and all of them can be addressed independently by the microcontroller. In addition, this whole address remapping we're talking about, this is where it comes into play. In this case, you have 3 camera units, and their address is all the same. What we're showing here is A0 as the address. Well, this gets remapped. Each deserializer is told, I have a camera with address A0 mapped here, but I'm going to call it something different. And the user assigns a new and unique address within the deserializer's registers to tell it and the microcontroller, hey, when you want to talk to the camera, use this new pseudonym, right? He's got another name now. But at the end of the day, it's all translated to send the data to that camera that has the address A0.
And why would they want to do that?
Well, this would be really important. Again, we're talking these multi-camera systems. If you want to adjust one camera, you want to turn one camera on or off, like you mentioned, this can be independently addressed rather than having the host controller send A0 out and all the cameras hear the same thing, right? So it's, I can talk to Tom and I don't want Alex to hear, right?
Wait a minute.
So, so that's the
One
idea.
camera's getting the dirt.
Yeah, there you go. So that's really the benefit that this brings.
I see.
And then the second thing that we want to point out here is you can see these 3 GPI signals that I've identified. In this case, we've selected these, programmed these to be GPI on the deserializer and GPO, general purpose output, on the serializer. And again, this is tied in with synchronization. If there is, for instance, a frame sync pulse like we've shown here, the processor can say, here's where I'm defining my start of frame. All you cameras, I want you to align to this. So this frame sync pulse is transmitted from our deserializer over this low-speed back channel. Remember, it's continuous, so this frame sync pulse can happen at any time. It's not constrained by the data coming in. And then the frame sync is sent out of the serializer to the camera. All the cameras get the data at the same time from this initial frame sync pulse, and they can all align and then send their data back in relative synchronization.
And that gives you a potential, depending on your application, you might be able to reduce or eliminate buffers.
Right.
You might be able to improve the performance of your application just because, like I talked about with the stereo camera and other things where you're using some sort of signal processing, the more aligned your images are, the better results you get.
Okay, so the main point you really want people to take from this slide is that these parts are ideal for complex systems like
Exactly.
this. Okay.
Yeah, you've got it.
That's right.
Great.
Okay.
Another question that came in
Sure.
real fast. The question is, do we have a MUX solution or recommendation for multi-camera solutions if they want to select which camera stream comes over a single FPD-Link III cable?
Well, I think that's kind of what we just talked about.
Okay.
The address remapping is really meant to replace the use of a MUX so that they can have the microcontroller talk directly to a single camera on a single link.
Okay.
And just to summarize, the FPD-Link III parts really are designed for automotive systems, ground up. The key advantage is this single pair, video and bidirectional control channel on one pair. And these 2 chipset families support both 14-bit or 18-bit image data, really depending on the needs of the application. There's optional GPIOs for additional sync or control signals, and it has an I2C control channel that supports up to 100 kilobits per second, which is the typical I2C control rate for these type of applications. It has low latency control channel, no waiting for the blanking, and as well it has a lot of the features that really have been defining our product family from the beginning. Signal conditioning for extended reach. In this case, because of the pixel clock frequency, it supports up to SVGA for both imagers and displays. And like we mentioned before, very importantly, these are low EMI solutions. They're proven, reliable, and robust for automotive applications.
Another question that came in, how about multiple cameras sitting on a single link and you need to select which stream comes across?
Well,
Yeah, so each camera will have its own independent link.
Okay.
So that really, I guess, kind of answers the question is each camera will be assigned to one serializer, deserializer pair.
Okay.
You won't have necessarily multiple cameras sending video data to a single serializer and deserializer. Now, if I can just take the question a bit further, I think maybe you're asking about having multiple I2C devices sitting off of that serializer on the remote side. And absolutely, all of those can be addressed. What's done when the system is set up, you'll configure the deserializer, set some registers to let it know what slave devices are out there. And you can have, I believe it's up to 8 slave devices. So whether they're cameras or additional devices, temperature sensors, anything.
FPGA,
Yeah,
anything that you need
else,
there.
any other I2C slave devices can be addressed directly by the controller, and then that data is routed through the deserializer serializer pair, and then back to those slave devices.
Okay, great. Thanks.
Sure. Okay, ready to move on?
Right. So we've told you about the FPD-Link III technology, and we've told you how it's used and what applications it goes into. Now we're going to tell you a bit about the great tools and support that we have to help you evaluate and to help you evaluate the systems. And that includes some of the basic stuff like the data sheets for the DS90UB 901, 902, 903, 904, the webinars like this one, but also there's a series of boards that are developed. Some are evaluation boards that allow customers to get the systems in their, get the chips into their house very quickly to set it up or look at it in different situations. And also we've got demo systems that help people understand the overall usage of these parts. And I'll let Sue talk in more detail on that.
Yeah. So a couple things. Alex just mentioned the evaluation kits. We have two types of evaluation kits. The first is really the product level evaluation. And this is similar to the kits we've had for our FPD-Link II devices, where it just consists of some headers, some control pins, and being able to really exercise and test out the serializer and deserializer pair. And the other thing that we're making available is basically a kind of a camera-specific evaluation kit. There was a question, are we working with any of the camera suppliers? And yes, we are. This one is uniquely defined to interface with OmniVision's camera development kits. So you can get the OmniVision sensor and controller board and insert our serializer and deserializer board in the middle. The connectors are all there, they're compatible, just plug and go. And then talking a little bit about development systems and demo systems. As I just mentioned, there's the OmniVision image sensor setup, and this is just a quick demonstration showing how this could be set up. You have the image sensor on both sides, or the image sensor and the OmniVision USB board, and you're inserting the serializer and deserializer in the middle. And just using the tools that come with OmniVision's development kit, you can actually run the full camera system. And we've actually had customers who like to use this not just as a point evaluation, but to set up a number of systems and do their prototype evaluation. They don't even have to develop their own hardware to see their system working.
This approach has been very popular. This is an extension. We already have similar devices available for customers to purchase off the web for the older products, the DS90C 241 and 124. And really the idea is that you have the existing OmniVision sensors and controllers, and you can put our cabling in there without making significant changes to the system. It's been very easy for people to use and get a prototype.
Great. Does this only work with OmniVision?
Yes, it does. This particular kit is specifically designed to work with the OmniVision sensors.
But the parts.
But the parts themselves work with any image sensor. Yeah.
Got it. Okay.
Okay, and then finally, this is kind of a cool one. We'll be talking about all these multi-camera systems. This is a multi-camera surround view demo. So this will be available for National to come out and show to our customers and show them an example of how a multi-camera system would work.
We're very excited and proud about this one.
Very cool.
Yeah, and so this is just a little diagram showing how this is all put together. Basically, we're using, in this case, there's the option to have 6 of our cameras connected. So we're using, in this case, it'll be an OmniVision camera connected to a serializer. So we've got 6 of these boards going to an intermediate board, which contains 6 of our deserializers, so 6 of our DS90UB 902. And then that in turn connects to a Xilinx board with image processing. So this does some of the stitching and surround view that Alex was talking about earlier. And then there's the output port over DVI or VGA to then put this onto a monitor and actually see what the image looks like coming from these multiple cameras.
Fantastic.
Yeah, very exciting.
Yeah, very exciting.
And so that gives you an idea of the different technologies, and the different evaluation boards and demo systems that we have coming to support the introduction of the new FPD-Link III parts. But what I'd like to...
One question real fast, just back on the previous slide. When is this going to be available?
So the demo systems will be coming out later this, later this fiscal year. So in the coming months.
Okay.
And we'll go into a little bit more detail on that farther on.
Okay, great.
So to give you the context of where these parts fit in the family of parts that we've released, the new parts now are the DS90UB 901, 902, and the 903, 904. And as we talked about, the key features of these are that they go over 2 wires for both the video and the control, and that they have the camera-based, for the 901, 902, they're targeting camera-based applications. 903, 904 is really targeting touchscreen. But if you look, this is the extension. The last parts we talked about were the 905, the DS90UR 905, 906, 907, 908. I know our NSIDs are a mouthful, right?
They are.
And what those targeted were infotainment systems for high-resolution displays. And they had a superior EMI technology to help improve the performance of the systems. If you go back further, there was the DS90UR 241 and 124 that's used in many systems, and that's 18-bit with strong, good EMI performance there as well. There was a set of products, the DS99R 421 and 124, that do conversions to support native FPD-Link III devices. So devices that either generate the FPD-Link III signal or receive it.
FPD-Link signal. Yeah.
And then the DS90C 241 and 124, which are in many camera applications today. So now that you've seen how you can use these new FPD-Link III parts, you know about the different collateral, evaluation boards, demo boards. I'm sure you're really excited, and now you want to know, how do you get more information? What's the next steps? Well, of course, the first thing you can always do is you can contact your local national rep or a distribution, however you normally get products from National Semiconductor. And particularly if you're interested in some of the demo systems we talked about that we would have to come and actually provide to the customers. Also, there's material immediately available on the web that you can rush off and check out. Product folders for each of these parts, and we show the list of the URLs for the 901, the 902, the 903, 904. Additionally, we have a displays feature site that talks more detail about how to use FPD-Link II and FPD-Link III parts in displays, and an automotive site that really is specifically talking about automotive, and that includes not just displays, but also cameras and other material like that. And because you're looking at this from an automotive perspective, the other question is AEC-Q. We didn't touch on it in a lot of detail in the webinar, but all of these parts are built from the ground up to be AEC-Q 100 qualified. We understand that that's a requirement for automotive applications, and we've got a site and a link where you can, where a customer, you can go and take a look and see how we do that and what it means for AEC-Q 100 qualification and National Semiconductor. Thank you very much for your time. We hope that you learned a lot today, and that this was a good introduction to these new parts that we're taking out.
This was a great session. Thanks to both of you for joining us, too.
Absolutely. Thanks for setting it up.
No problem. There is an assessment associated with this webinar as well. If you can take a few minutes to complete that and test what you learned in today's session, that'd be great. We'd also love your feedback. Also, there's an evaluation. You can take a few minutes to complete that. We'd love to hear your thoughts as well. So thanks again. Enjoy the rest of your day.